this one's going to be a tutorial on binary search trees, and I suppose that it's going to be a bit involved, so we'll just take our time and go through everything bit by bit. So I think a natural starting point would be binary trees, and they're really quite simple. It's just some node, right? And every node is allowed to have at most 2 children. So a left child and a right child. That's quite literally what a binary tree is. And so you can imagine that this is a node and it's allowed to have at most 2 children. This is also a node, and you can also have a single child as well, right? The only constraint is at most 2 children. And you've already been introduced to trees in general when we did our breadth first search video, and you saw that pretty much any graph structure can be encoded into an adjacency matrix, right? So you might be wondering, well, why don't we just do that here? And it's actually not optimal, not ideal either, right? Because it's going to be a very sparse matrix. So you're wasting a lot of space, and it's just not good. It's much better to do it like this. In this implementation that I'll be showing you, just use a structure to represent the node. You don't have to encode the entire thing into a matrix. Okay, so what is a binary search tree? So a binary search tree just extends from a binary tree. So it is a binary tree, right? But it's got some special properties to it, and well, just one special property to be honest, and that's the left child, for instance, right? Is always less than the parent node, and the right child is always greater than the parent node. So that's quite literally it. Okay, so let me walk you through an example with inserting values into a binary search tree, and hopefully it gives you a clearer picture of what's happening. So you might imagine then from our linked list videos, right, that you always have some node here, your head for instance. If you initialize a linked list, you have a null reference to the head, right, to start it off. And so, same thing here really with a binary search tree, but instead you start off with a null reference to the root of your binary search tree. So instead of it being called the head, it's called the root, right? And it serves as the entry point to your structure, okay? And so it's quite similar to a linked list if you think about it, right? The only difference is instead of just having a 1 pointer to another node, it has 2 pointers, okay? And so that's a little difference there, but if you want to think about it as a glorified linked list, feel free to do that, right? Okay, just so long as you understand the ideas. And so imagine then that we inserted the number 10, right, first. Then 10 would become the root node, right? And then suppose we wanted to insert the value 11. Well, you would have to ask yourself then, is 11 greater than 10 or less than 10, right? Remember the special constraints that are on the binary search tree. Well, it's greater than 10, so it goes to the right. And suppose we wanted to insert 5, and then 5 is less than 10, it would go to the left. Now suppose we wanted to insert the value 3. 3 is less than 10, so it would come here, right? And then, but there's already something here, there's 5 here. So then you'd ask yourself the same thing then, okay, well, is 3 less than 5 or greater than 5? Well, it's less than 5, so you come here. Right, and same thing again, suppose you wanted to insert the value 2, right? 2 is less than 10, 2 is less than 5, 2 is less than 3, so 2 would come here. Right? So hopefully that's clear enough to you, and you understand the gist of it then. So I suppose we can get straight into the implementation, and then we'll take it from there. Okay, so just standard stuff here. And I think we need standard limits. We'll definitely need this. Okay, dollar signs is supposed to be there. Get main out of the way, and it just returns 0. Okay, fairly simple so far. Well, now we just get to the structure itself, so we'll define a structure. It should already be very familiar to you. So it'll just be, we're going to try to get sort of an implementation that's more or less modeled after the real world, right? So you could typically use like an integer to be your key, but we'll use a char. So we'll use characters then, and you can obviously add more elements to your structure as well if you like. So we'll go with fname, lname, and then we're going to need a pointer to the left node, or the left child, right? Pointer to the right child as well. And then we also need a pointer to its parent, right? And you'll see why this is important when we get to operations pertaining to deletion. And pay attention here as well that we had to use this forward declaration here, right? Because we're referencing the node itself before the structure has been instantiated, so it's important to have this forward declaration here in this particular case. Okay, so let's just go with, since we already have that, we can just go ahead and say node star root is equal to null. Set that off straight away. And then let's get a function to create a node. So we're just going to need first name and last name, right? Okay, pretty simple stuff. And node star new node. All of this should be quite familiar to you already. Node pointer, call malloc, then size of node, right? Okay, well this bit here might be a bit esoteric to you if you're now seeing it, but hopefully the pattern becomes clear. So it's going to be size t, fname length is equal to, and then we'll call string length on fname. So all this is doing is it's going to get the length of this parameter, first name, right? It's going to store it into a variable called fname length, and it's of type size t. Size t is just an unsigned integer, so if you don't know what the difference between a signed integer is and unsigned integer, feel free to check out my second video in my digital logic series. I went over that there, so I think if you just segue to that and then come back here, you shouldn't have any big issues there. And so you do the same thing for the last name as well. So lname length, and then lname. Now what we're going to do is, so I'll say new node dot fname, right, is equal to, then ***, and we're going to dynamically allocate some memory to hold an array of characters essentially, and it's going to be of size fname length, right, +1. Now you'll see why this +1 is important in a bit. So we'll copy this and paste it here as well for the last name. Last name, and here we go. Okay, and so all this is doing really is, suppose that the fname, for instance, right, was 5 characters long. Malloc is going to generate, right, size of, right, and so size t is the parameter that malloc expects, and so what you're getting in here is going to be, for instance, right, if you put in 5, some string then that was 5 characters long, it's going to return it here, right, and then it's just going to be 6. 5 plus 1 is 6, right? So yeah, you're going to get a total of 6 elements here, so you have an array capable of holding 6 characters, but remember, right, it's just a chunk of memory somewhere, there's nothing there. Okay, there's nothing there as yet, so we have to copy something into that memory, and that's where we use string copy here. Okay, so we're going to say string copy, and I think the way string copy works is destination and then source. So the destination obviously is new node dot first name, right, and then the source would be first name, and then we do the same thing as well for the last name. This comes here, and last name. Alright, and so you might be wondering still, well, what the bloody hell is this +1 doing here, right? Well, what string copy does for you, right, it's going to take this parameter, suppose then it was 5 characters long, it's going to copy it, and it's going to copy it along with a null terminator for you. Just remember, every string needs to have a null terminator at the end of it, so you need to account for that. And string copy is quite helpful in that manner, right? It's copying the null terminator for you. Alternatively, you could have come up here and declared some array, right, to hold an array of characters, and it's going to have to be fixed size, right, maybe 100 or something like that, and then you can use string and copy to manually put in the null terminator if you wanted to. That's just not pretty, if you ask me. You can do it, right, and I've done it myself, so, but I think this is by and far a more flexible solution, and I don't see a case where you'd want to use the array over this particular implementation here. But I'm sure some niche case might come up, but as far as I can see, or as far as I've experienced, this is by and far just better. Okay, and then we're going to say new node dot left, right? Set it equal to null. Same thing for right. Set that equal to null as well. And then the parent is null as well. Then finally, when we're done, we're just going to return the new node. Okay. There we go. So that's our create node function. Now we need an insert function. So we'll say node star insert, and it's going to take pointer to the root and just the first name and the last name, right? Name, char, last name. There we go. Okay, and we're going to take a recursive approach, and so I'll code the function out first, and then I'll go over with you. And I think I'll have to do the in order implementation as well, just to test that it works. So okay, we'll start off by saying, okay, if not root, so if the root doesn't exist, right, this is going to be our base case, and we're just going to return, create a node and return it to the caller, and it's just going to take first name and last name also. Yeah, I think that's fine. And then we're going to use string compare, right? So remember we said that when we're inserting a value, for instance in the examples we were just inserting integers, right? Then you would have to compare the integer to the node, right, that you're inserting into, to see if that integer is the child node, that is, whatever integer you're inserting, if it's less than the parent node or greater than the parent node, and that would determine if it goes to the left or to the right. And so with a string, however, what we're going to have to do is use string compare, right? And what string compare is going to do is it's going to compare string 1 and string 2, right, lexicographically, and then, so string 1, string 2, and return greater than 1 if string 1 is greater, right? 0 if they're equal, and less than 1 in the other case. Okay, so string 1, in this case, we can set it equal to root dot first name. We're going to use the first name as the key, right? And then we're going to compare that against the first name. And so if the first name in the root, right, parent is greater than, it's going to be greater than 1, right? Oops. X is going to be greater than 1. So we're going to say if x is greater than 1, oops, if x is greater than 1, or 0 rather, if x is greater than 0, right, then what does that mean? It means then that the root node is greater than the node that you're inserting, right? So it has to go to the left then, right? Okay? If the root node is greater than the value you're inserting, that means it has to go to the left. Hopefully that makes sense. It means it's less than the root node. Okay, so we're going to say root.left is equal to insert, and then we're recursively calling the function on itself here. So we'll say root.left, fname, and building. Okay, and then let me just put a note here, add parent, and I'll put that later on. But for now, I just need to ensure that we got this covered. Then we'll say if x is less than 0, this is the other case. Then we'll say root.right. Same thing here, insert root.right, and first name and last name. So, just put a comment here, add parent in. Oops, I can't type. Don't have my keyboard. I'm typing on this laptop keyboard for longest while. I just can't get accustomed to it. Because the keys are just so small. I'm so accustomed to just typing on this big keyboard, but it's fine. Then at the end, we can check for the 0 case as well. So we'll say if x is equal to 0, that means that it's a match, equal to 0. In that case, just return the root straight away. So by the way, binary search trees don't have duplicates inside of them. Just wanted to put that out there. If you wanted to keep track of duplicates, I suppose you could go up into the structure itself and add like an integer count or something like that. But if you put in a duplicate value, and there are like structures that will account for duplicate values, just not your typical binary search tree, because that breaks the fundamental property or constraint that we were explaining, right? If it's the same as another node, then we won't know if to put it to the left or to the right. Okay, and that's just a fundamental constraint on the binary search tree. So if there's a a duplicate node, we don't do anything. Or if you want, you can update that node if you would like, right? But just don't try to add it back in there. Okay, and then at the end we'll throw the root back to the column. Alright. And so I suppose I should test this first, and then I'll explain how this works. So we'll say root is equal to insert. And we're gonna go insert into root, and we're gonna say A, and nothing here. Then we can call insert again like this. And you're probably wondering, well, why isn't it root equal to this time? You could if you wanted to, but it's not necessary, and I'll show you in a second. Just root, let's insert B, and I don't know, nothing here. Alright, let's try compiling this. We don't get any errors, which is good news. So I'm wondering if to just go ahead and implement, I'll implement the level order as well, not level order, the in-order traversal, just to ensure that we're getting something here, and then I'll go back and explain how the insert is working, and then we'll do the level order as well. How do I keep saying level order? In order. Okay, so void in order, and it's just going to take a reference to the root node. And all it's doing then is that we'll say, as our base case, it's a recursive implementation as well, and you'll see why recursion really is a natural thing to use when you're dealing with tree-like structures, because the call frame itself will resemble the tree. You'll see this. Okay. So as long as it's not root, or if root rather, if a root exists, then we're gonna say in order, call in order on itself. Root dot left. Done, print that value out, so we'll say %s and root dot fname, and then we'll go in order root dot right. Fair enough, yeah? There's no big issues here, and then let's just test that it works as expected. So this should just print A and B, so we'll say in order root. See how this goes. Yeah, A and B, and let's just change up the ordering a bit, so we can start with like something like B, A. Let me just copy this and paste it here. Put something else in. Maybe C, right? B, A, C. So it should print A, B, C regardless. I don't think that's saved. Yeah. A, B, C. Okay, so the in order traversal works, and I think we don't have any issues so far with our implementation. So let's forget about this for now. We'll come back to how to play how this works, but let's start with our insert function, and then we'll walk through what happens, right? And so essentially, inside of our insert function, we get green. It looks like this, right? Function looks like this. The first case is checking for null, right? If you look here carefully, it's checking that not root. Not root means that it's null, essentially, right? There's nothing there. So it's checking for a null case. And then the second time, it's checking if it's greater than, the node that you're inserting is greater than the parent, right? So essentially, if that happens, that means the node you're inserting is less than the parent, right? Okay? So if the parent is greater than the node that you're inserting, rather, I should say, that means it's less than the parent. Hopefully I didn't convolute that too much. So, okay, node you're inserting is less than the parent, or node you're inserting is greater than the parent, okay? And you can obviously switch this logic around the other way if you wanted to as well, whatever you feel is comfortable for you. But this is essentially how our function goes, right? Null case, less than, greater than. And then at the very end of the function, we're always returning the root. If you look here, we're always throwing the root back. Okay, return root. So let's walk through our example here. We're not going to use letters, we're going to use numbers, but you can abstract very easily how it's going to operate with letters as well, especially with the first name as the key, right? But we're going to just stick to integers for now, just for simplicity, okay? I don't want to be taxing my brain. It's not that hard anyways, but I'm just lazy, man. So let's start off with a number like 10, right? Okay, so remember then that we initially set the root to be null at the bottom here inside of main, right? Root starts off as null, right? So that's what happens. And then suppose then we set root, right, is equal to insert root, and then we put in some value, right? So suppose we wanted to insert the value 10. Okay, what's going to happen? Then it's going to run, right? And it's going to see straight away that root is null. that there's nothing inside of the root. And so what it's going to do is it's going to return, it's going to create the node, and it's going to return a pointer to it straight away, right? And then what happens is that it's going to get assigned to the root here, all right? And so it's very important on the first iteration that you assign that value into the root. Otherwise, the root is always going to be null, okay? So you only have to set the root once, and then you don't have to keep updating the root after that, right? The only time you're changing the root, I suppose, is if you're removing the root node, right? But that we'll get to that in the deletion operations. Okay, so this is what happened, right, on the first bout. So we inserted the value 10. So 10 became our root node, then essentially. So 10 was our root node. So we got this. And so it created this root node, and then it created a left and a right, null and null. It also created a parent node and set it to null as well, but we're not doing anything with the parent nodes yet. We'll come back to that in a second. Okay. So, great. We've got the root node inserted. Now suppose we wanted to insert the value 11, right? What's going to happen? Well, it's going to come up here and it's going to say, okay, well, we've got a root node, so it's not going to bother with this, right? Then it's going to come here. Well, in this case, we're checking now, right? So you're checking whether or not the node you're trying to insert is greater than the parent or less than the parent. So in this particular instance, it's greater than the parent, right? So since it's greater than the parent, then you would run this case here, right? So root.right is equal to insert root.right, okay? So root.right now is the new root node that you're inserting from. Okay, so this null value here, root.right, is currently null. So we're inserting that, right, into the new function call, okay? And then it's going to come up back here and it's going to see that it's null, right? It's going to see that it's null. And it's going to throw that back to the caller. Okay, so let's see here if I can draw this in a better way. So the first function call, right? First function call happened, and we saw then that it wasn't null, right? It wasn't null, and we saw that 11 is greater than 10, okay? And so we went ahead and called the root.right portion, right? So we're making calling another function now, root.right, okay? And then when you call that, it's going to return, right? This case here is going to trigger and it's going to return. It's going to create that node and it's going to return it, right? It's going to return it. So that's all it's doing, really. So it called that create function somewhere, and then it returned the value back, right? And so that value is just coming straight up back to this guy here. Okay, so it's being returned back to this function here, which called it, right? And so it's here now, right? It's been returned here, and so root.right will be set. So this value here now is being set, okay? Or this value here is being set. Hopefully that's clear what's going on there. So this would be 11 here. All right, and let's go one more iteration, and let's do 12. Let's insert 12, right? So what would happen if we inserted 12, okay? Okay, so the function would start, right? We would see that it's not null, right? And then we'd see that 12 is greater than, okay? So it would call this guy here, right? And then, oops, okay, it doesn't matter actually. Yeah, so it would call this guy here. So we've got another call frame, right? And then we'd come up here and see that, okay, well, it's not null, right? Root.right is no longer null like it was in the previous case. It's no longer null. Okay, so it's going to come down here and it's going to compare then now. Is 12 greater than the root, right? Which it is. 12 is greater than 11. So it's going to call another, right? Another function is going to call, okay? With root.right now being the new root caller, the new root node, right? Which is null. And so the base case is going to trigger. Right, so every time it encounters null, the base case will trigger, and it's going to return it back to the caller. So this is going to return back to this guy here. This is 11 currently, right? And so 11.right is going to be equal to whatever this function returned, right? Remember, it created that node for 12, and then it sent it back. And so 12 is going to be put in here, essentially. Okay? And then what's going to happen is, once that's done, this is going to continue executing. So we're in 11 now, right? We're in the 11 function call. And it's just going to continue onwards, and it's going to return the root, right? So it's going to return 11 back to the caller, right, which is 10, right? It's going to return 11 back to 10, right? And that's going to be this portion here, the same root.write, and it's just going to get assigned again here, all right? And then this is going to return the root outside, and this is the first, like, whatever, insert. This is the insert. Okay, yeah, right? And so that's why we were able to assign the root outside here. Okay, so the insert function was holding the first root, okay, or your main root value. So hopefully it's clear to you how the insert function is working. And let's go over the in-order traversal now, and I think you'll get an idea then of how that, but you can already see then that recursion is forming a tree-like structure that, you know, pretty accurately describes exactly how our binary tree should look, right? So let's create a new page after, and let's go over this in-order traversal here. Okay, so how this is going to work, right, is first of all, it's checking that the root value isn't null, so that's our base case, right? And then it's going to call in order here, it's going to print a value, and then it's going to come here. So let's come up with a contrived example, and then we'll see how the in order function operates on it. So we can start with 10 again, right? Then maybe 5 here, I don't know. And then maybe 11 over here. And maybe 4 here. And I don't know, 2. So 2 would come here, 2 would come here, and then 2 would be here, right? And I think maybe I should put one more in somewhere here, or here. I don't know, to the right maybe, right? So 6, yeah, 6 is less than 10, and 6 is greater than 5, so 6 would come here. Okay? So this is what we're dealing with in our structure. So this would, this null value sitting here. Null, null. This is null, and then 2 null values here as well. So this is our complete tree structure. Okay, and let's try to traverse this using in-order traversal. And I'll show you exactly how recursion works here. I think you should probably get an aha moment if you've never had that. Alright, so I think again it's helpful to understand. Let's just draw our function here so we can keep track of it. So the first thing it's doing, right, is it's checking for null. Again, this is our base case, right? Okay, and then it's going to go root.left, right? Then it's going to print some value, and then it's going to go root.right. Great. Okay, so that's our function stack, if you want to call it that. I just you know, made up a stack here to keep track of our function. So what's going to happen then on the first bout is that we're going to call in order onto the root, right? And it's going to see obviously that it's not null. Okay, so first function call is on the root, so this, we're in the first function call now, right? And then it's going to go to the left, right? So it's going to call in order on itself for root.left, right? So it's going to make another function call here. Okay, it's going to see that it's not null. Then it's going to make another, so we're in a new function call now, right? And then it's going to go to the left again, right? It's going to see that it's not null. So this is 10, this is 5, this is 4, we're at 4 here. And then I'm going to go left again to 2, right? It's going to say, okay, well, 2 is not null. Let's go to the left again, right? And so finally now, it's null, right? So if it is null, nothing here is going to run. When it's null, nothing inside of here runs, right? You can see that here. So, okay, if the root, only if the root exists, run this code. Otherwise, don't run anything inside of here. Okay, so it's not going to run anything, and it's going to go out of scope, and it's going to return to the caller, okay? And then what happens next, right, is it's going to print the value out now, because we're done going to the left now. So it's going to print that value out. So it's going to print 2 out, okay? It's going to print 2 out, and then it's going to go to the right, okay? It's going to go root.right, like so. And it's going to come across a null value, so nothing is going to run, right? So that's going to go out of scope and return to the caller. And finally, now everything inside of here is finished, and so this goes out of scope and returns to the caller, returns to 4, right? And so now 4 is here, right? 4 is here, and so now it moves on, right, to the print portion, so it's going to print the 4, right? And then it's going to go to the right then. So we're finished printing, it's going to go to the right, and it's going to find 6, okay? So now we're in this function call here, and it's going to see that it's not null, so it's going to go to the left of it, right? So, well actually, no, 4 here in this case is null, so that's my bad right there. Where's my eraser? Eraser. So 4 in this case is null. Okay, so it's going to meet null here when it comes here. So nothing is going to run, and it's going to return to the caller. Alright? So it's going to return back to the caller. So I'll print the 4 out, it'll go to the right, okay, and it's going to return back to the caller. This is going to go out to scope and return to the caller. And then this goes out of scope and then returns back to the caller here, which is 5, right, which is then going to print the value 5 out, because we're done with the less than, we're now with the print, right? Then it's going to go to the right, okay, and then it's going to, so we're in this one now, we're in this function call here, right, and then it's going to say, okay, well, it's not null, let's go to the left, so it's going to come to the left, and it's going to see that it's null, right? So nothing is going to run, it's going to return to the caller, right? And then now it's going to print the value, we're finished with the left, it's going to print the value, 6, right? And then it's going to go to the right, it's going to see that it's null, and so it's just going to return back up here, and then finally 6 goes out of scope, and we come up back to 5. Alright? And then for 5 now, we're done with the right, so this goes out of scope, 5 is finished running, and then finally this returns back up to 10 now. We're back now into the original first function call, right? This one here. So we're done with all the left. We're done with the entire left subtree. Can you see we've traversed the entire left subtree? Okay, and then now we're at the print portion. So it's going to print 10, right? And now it's going to go traverse the entire right subtree. If there was more here, it would traverse the entire right subtree. And so it's going to make another function call here. And this one's going to be for 11, right? And then it's going to go to the left, right? And it's going to see that, well, it's null, so nothing, return back to caller, print 11, then go to the right, it's going to find null, return back to the caller, function finishes running, goes out of scope, return back to the caller, and then finally our original function call goes out of scope as well, and then we're done. And then can you see then it's traversed everything in order, right? So 2, 4, 5, 6, 10, and 11. Hopefully you can see that. And look at it, right? The call stack, right, or the call frame, it's literally our tree structure. It's the same thing, right? That's why recursion really is such a natural thing to use when you're dealing with this data structure here, or tree data structures in general, I should say. All right. So I hope you do see that. That's what the main point that I was trying to get across there. All right. And there is something else that we need to take care of, and that's to do with the parents, creating the parent node. So we have to create a parent node here. So we'll say if, right, root.left. If root.left exists and it doesn't have a parent, so root.left. Okay, then we're just going to say root dot. How do I do this? So, oh yeah, so root.left dot parent is equal to root. Set it equal to the root node. And then we do the same thing here. So let me just yank this line, paste it here. Oops. Not sure what happened there. Okay, and then okay, so then this would just be root.right. You just change it. Root.right parent. And I think it's probably helpful then if we just go through this one more time. And I'm really just taking my time to go this over with you so you can see what's going on. I don't want any ambiguities at all when it comes to binary search trees, because if you have ambiguities in implementing a binary search tree, there's no way in hell you're going to be able to implement the AVL tree at all, right? You just have to fully understand and fully grasp everything that's going on, especially inside of this insert function, because all the AVL tree is, right, is an extension of the binary search tree implementation, and it's going to be doing balancing. So we will get to the AVL trees in some other tutorial, but for now just focus on the binary search tree, ensure that you understand this well. So that's why I'm taking my time again. So we're gonna do another contrived example, or we can reuse our contrived example up here from our insert, but already it's messy, so let's just start over. Okay, so let's put this here. Alright, so suppose then that we inserted 10, right? We're starting with null, and then we're inserting 10. So this would be 10 here, right? It's got left, it's got right, and then what's going to happen? Nothing happens, right? The root node, the parent of the root node is still null. We haven't touched that, and that's a very important property, right? So the root node's parent, the root node has no parent, right? So it makes sense that it's null, so bear in mind, keep that in mind. Okay. And then now we're going to insert value 11, right? So 11 is greater than 10. Okay, so our call frame is going to look like this. It's going to start with this 10 here, right? And then it's going to say, okay, go call something else, right? Root.write in this case. Okay, and then so it's going to call root.write, and that's going to encounter the null case, right? As we already went over before, right? So it's going to encounter the null case. So this is going to encounter the null case, which is going to throw that back, right? So it's just going to return straight back to the caller. It's going to create that node and return the pointer straight back to the caller. And so then we're setting root.write inside of this caller here, 10. So we're setting 10.write to be equal to whatever pointer was thrown back to us, right? And so in this case it was 11, right? And so 11 was created and put here. Great. Now what the bloody hell happens after that? Then we check, right, if root.write exists, right, which it does now, right? It exists now because we literally just created it. Then what we do, right, forget about this part for now. What we do is we set root.write.parent, right? Root.write.parent, this guy's parent, we set it to the root node, right? And we're in 10, so the root node is 10, and the parent of 11 is 10. I hope I'm getting that point across, okay? And so, yeah, that's pretty much it. And then this not root.write.parent, right, what we're doing here. So we're checking, right? So we're checking to ensure that it doesn't have a parent, because remember, this is a recursive approach. So this bit of code, if we didn't put this check here, is going to run every single time we insert a value, and the call frame started getting really deep, right? It's just gonna keep inserting the parent every single time. We don't have to do that if the parent's already been inserted. So we just check that the parent hasn't been inserted, right? And so if the parent is null, then only then we set that value, okay? So that's why we're putting this here, to just save ourselves a lot of computational power. And the same thing is going to happen for root.left. So I just showed you the case for the right side, and the same holds true for the case on the left side as well, right? So hopefully that's clear here. And so then this would finish running, and then, okay, this is going to return root, right? The root is just, the main root here is going to be thrown out back to us. And we're not doing anything with that though. Only in the first instance of this program, we're setting whatever this threw out back, we're setting it equal to the root, right? But we don't have to set the root every single time, just the first time, as I already explained. Okay, so hopefully you're following along. And if you're following along up until this point, I think you're doing alright. Alright, then, so I think we can move on to level order traversal, and you've already been introduced to level order traversal, by the way. In our breadth first search piece of code and explanation, you saw that we use which data structure, if you can remember? The queue, right? And so we're literally going to be using a queue to do level order traversal. And hopefully you watched that video and you understand why the queue gives us traversal by levels, right? Okay, so let's go ahead. And so we have the in order, we're just going to do level order now. I'm going to take a bit of a lazy approach to this one. And so, yeah, I'll explain the code obviously, and you can use a linked list to implement your queue if you'd like. You don't have to do it this way, but okay. I'm getting fed up, and so whenever there's a lazy way, you do the lazy way. Okay, so we'll say void level order. Oops, where's my caps? And so obviously we need the root, and yeah, that's all we need really. The root, that's about it. Right, and so we're gonna check first, obviously, first of all, if not root, if the root doesn't exist, right, just return straight away. Just want to get that case out. Right, so what we're going to do is we're going to say no star star q. I'm going to explain this in a bit, but it should be clear to you what this is doing anyways, but whatever, I'll explain it. Malloc, and it's going to be 1000 times size of node star, and then finally you typecast, right? So typecast to node star star. Alright, well, what even is this? So, the hint, right, or the devil's always in the details then. It's size of, right, node star, right? So it's holding a node pointer, right, times 1000. So it's holding 1000 node pointers. It's an array of node pointers. That's literally what it is. And if you go back to our pointer tutorial, I was explaining to you that every single array, right, some contiguous block of memory somewhere, the first element inside of that array, right, is a pointer in and of itself, right? Do you remember that if you dereference that array, you get a pointer to the first element inside of that array? Hopefully you remember that, and that's literally what it is, right? So you need a pointer to a pointer, because the array itself is holding a pointer, right? So you need a pointer to a pointer. Hopefully that makes sense. Let me try it. Maybe. Let me try. So you've got your array here, and this is a node, this is a node, this is a node, right? It's just node pointers. That's all it is, right? An array of node pointers. And so you need, obviously, to get access to this array, you need a pointer to a pointer. And so this here is literally node star star here, right? So it's a pointer to a pointer. And so it's a pointer to the first element inside of your array of node pointers. Yeah, I don't think I'm going to be able to articulate that any better than that. And by the way, you've already seen this in our hash table. You've seen an array of nodes before, or an array of node pointers rather, which can then be extended to an array of linked lists, right? Which is quite literally what a hash table is, really, in its essence. Okay, so that's if you watched the hash table video. But alright. So that's how we're creating our queue, right? That's how we're going to be creating a queue. And if you think about it, it's just not going to be as flexible as like an actual queue, right? If you were using linked lists that can dynamically grow, it's got a fixed size, but it's fine. And then we'll say integer front, set that equals 0, and rear equals 0. So this is how we're going to need two variables here to keep track of the position, right? Keep track of enqueuing and dequeuing operations, pretty much. And so we're going to say while. We need a loop now. So say while front is less than rear. That's how we're going to do this. Oh, before this, let's enqueue something in. So we're going to say queue rear plus plus is equal to and the root. So we're going to throw the root into the queue. And so what happens here, right? Let me explain this bit of code to you. It might look a bit confusing, but it really isn't. So it's going to go rear is 0, right? So it's going to say rear q of 0 is equal to root, right? And assignment precedence equal is higher than plus. So it's going to assign first and then iterate, okay? It's going to assign first and then iterate. So it's going to put the root inside of the 0th bucket, right? And then it's going to iterate the rear pointer, okay? That's how that operates. Hopefully that's clear to you what's going on there. And then we'll say node star current is equal to, and we're going to grab now from the queue, right? And we're going to say front plus plus, like so. Okay, so again, it's the same thing here, right? It's going to grab this value first, right? Do the assignment and then increment the pointer. Equal sign, higher priority than plus, okay? And I'm going to go this over with you in a bit. Just want to get the implementation out of the way. And so then we'll just print the value out. So we'll say maybe %s. So, and we'll say current dot first name, like that. And then now we're going to check, right? If current dot right. So if current dot right. So if there's something there, then I think all I have to do is, I'll just do it like this. We have to put it into the queue, right? So we have to enqueue it. So we'll say queue rear plus plus, right? And then set that equal to current dot right. Okay, hopefully this makes sense to you. So if there's something to the right of that node, right, put it into the queue. That's all it is doing. Then you do the same thing here for the left side. So if current dot left, you do very much the same thing. You enqueue it. And I feel as though this is a little bit backwards though, so let's do the left side first and then we'll do the right side. The order doesn't matter here, I think, but I just maintain the logical structure. I just, you know, intuition is telling me that we should do this. I don't know whether or not it makes a difference, but we'll see. My sense tells me no, my intuition just tells me to do it for some reason. Okay, so rear plus plus is equal to then current dot right. Okay, so that should be fine. I think this is just about right. So let me just test this out, and then we'll do a little bit of tidying up there. So we got in order, and then let's do level order as well. Oops, and let's see if we got any issues. So BAC, right, so level order works just as we would expect. Let's just comment out the in order traversal. Obviously though, it's not printing the levels, so we can fix this, I think quite trivially. So what I'm going to do is I'm going to come up here, I'm going to put a for loop. Yeah, I'm going to do it like this. Drop all of this inside of the for loop. And I'll go over the diagrams and stuff in a second. For here, so we'll start off here by saying draw equals 0, I is less than level, I plus plus, like so, should be fine. And then here I'm just going to say integer level is equal to, I think it's, yeah, we can subtract the front from the rear. This should be fine, or is it the other way around? We'll see. Yeah, it has to be the rear from the front, yeah, because the rear is always going to be, yeah, the rear is going to be in front of the, yep, that makes sense. And then here, after every single level, as it were, we're just going to print a new one. So it should, there we go. Whew. And let me insert something else just to ensure, oh, oops, undo. Let me insert BAC, D, and E. There we go. So it works. So yeah. So B would be here, A would be to the left of B, C would be to the right, D would be to the right of C, and E would be to the right of D, right? So it's working. Okay, let's go over why it's working and what's going on in a bit more detail. So I'll draw it to the right maybe. Okay, so we've got our array here, right, obviously. And we've got the rear pointer here, and we've got the front pointer here. And I'm just going to draw some values in. Let's use a contrived example. So let's use this data structure here, 10, 11, and 5, right? We're going to use this contrived data structure here. Okay, and we've got these empty chunks of memory here, okay, that we can put values in, put nodes inside of. So what's going to happen then, right? Let's go back in on the first bout, right? Front is equal to 0, rear is equal to 0, and so we're enqueuing at the 0th position the root, and the root is 10. So 10 is quite literally here. Okay, so we're enqueuing here, and so root, right, starts off at 0. Okay, so root starts off at 0, 0, 1, 2, 3. Front also starts off at 0, 1, 2, and 3. So at the beginning, both root and front are set to 0, right? But then we enqueued 10, right? And then we incremented the root the rear rather. So rear is now here at 1, right? The rear pointer is literally pointing here. Okay, and front is still pointing to 0, by the way. Okay? And then what's going to happen is it's going to calculate the level, right, by subtracting the rear from the front, and based on the level, that's the amount of time it's going to iterate this code in here. And so now, but the important bit though is just to grab the current, right? Grab what's in the queue and increment that pointer. So grab this value and put it into the current node and then increment front. So now front is sitting here as well, right? And then we print that value out, right, which was, well, we'll be printing 10, okay? We'll be printing 10, and then it's going to check then if there's a left pointer, okay, and if there's a right pointer as well. Or if there's a left node or there's a right node. Yes, there is a left node in the first instance. So what it's going to do is that it's going to put the 5 in here, it's going to enqueue the 5, and rear is now going to be sitting here, right? And then it's going to say, okay, yeah, well, there's a right node as well, so go ahead and enqueue that value as well. So 11 is going to come here, and then rear is going to be here at 3 finally, right? So rear is 3. Okay? Hopefully that makes sense. And so on the first bout, right, rear is 1 and front is 0, so it's just going to, this bit here is just going to run once, right? And then it's going to print the new line. Okay, so then we're in a new line now. Okay? And then it's going to come up back here and it's going to calculate the level again. And so what is rear though? Rear is 3, right? Rear is 3, and front is 1, right? So 3 minus 1 is 2, okay? And so the for loop is going to run a total of 2 times, okay? This is for the for loop here. Pay attention, the for loop here is going to run 2 times. Alright, so on the first iteration of the for loop then, it's going to grab the value in the current queue, right? So it's going to grab 5, right? It's going to grab 5, and it's going to print 5 out here, right? And then so it grabbed 5 and then it incremented the pointer. And so now we're sitting here at 11, right? And it's going to say, okay, well, there are no children, right? No left or right children, because we're pretty much done there. And so then, now it's going to come up back and it's going to grab 11, right? So inside of our for loop is counting 0, right? So we're done with 0 now, okay? And then it's going to come here and grab 11, right? So 1. So we're in 1 now, inside of the for loop. So it's going to grab 11, okay, and it's going to print 11 out, like so. Alright, and it's going to see, okay, well, 11 has no children, right? So, okay, that's going to be done running. And then finally, we're going to get to 2, right, in the for loop. And then it's going to increment the pointer again. Okay, so remember though, when it grabbed this 11, it also incremented here. So it's already pointing here. Okay, so it grabbed 11 and then it incremented. So it's here. Front is here now on the 3rd iteration of the for loop. Okay, and then it's going to increment the current again. So current is going to be equal to here. Right? See, it's going to come here and it's going to grab whatever is in front of that. In this case, it's null, right? Nothing is here. This is null. So it's grabbing nothing and putting into current. And then the pointer moves across, and this entire function here is going to come and finish executing. And then what happens here though? The while loop is going to stop running because the front variable is now greater than the rear, right? Or the front, while front is less than rear, so the condition is broken then. Front is no longer less than rear, it's greater than rear. Okay, can you see that? Rear is here at 3, and front here is now at position index 4. Okay, and so that loop is going to stop running, and so this is going to be the level that we had in that particular instance. But you can see the gist of how this algorithm is functioning, okay? And I hope I didn't do too terrible of a job explaining that. Insert page after. Okay, so I think you've got already a lot of strong elements. You know the structure, you can create the node, you can insert the nodes, you can insert with a parent, which by the way is a very important thing. Do not underestimate how difficult it is to figure out how to insert a parent. And you might take it for granted, but if you had to come up with this on your own, it'll take you a little bit of thinking, but as long as you've seen it, right, you can obviously then reverse engineer and figure it out for yourself, okay? But I'd highly recommend you try to just don't memorize code, don't memorize anything. Try to learn the concepts and then apply them yourself, right? Code everything as I'm doing here, just code it out from scratch, right? Try to figure it out for yourself so you can sort of reinvent anything on the spot, right? You're not dependent on your memory. Sure, your memory can help you along the way here and there with pattern recognition and things like that. It'll aid your problem solving, but it shouldn't be your only means of problem solving, okay? Alright, so now we've got to get onto a pretty big topic, and that's deletion. Okay. I'm sure this video has already gone on for a long time. I'm getting a bit tired, but I'll press through with the deletion. We can call it wraps there. Once you can delete, I think you're good to go. Alright, so when deleting, right, there are a lot of fringe cases you need to consider and things like that. So let's start with the simplest case, right? So suppose that this was our structure here. So the first case, right, when you're deleting a node is when, suppose then that this was the node we wanted to delete here. We wanted to delete this guy, right? We can see that it has no children, right? That's the first case, when a node has no children. That's, okay, it's pretty simplest case, I think. How would you go about deleting this node? Right, maybe you should think about that for a second, but it's not as difficult as you might think. Well, first of all, you need a function to find nodes, right? So we should actually, before we come to deletion, let's implement the find node function, because it's quite important. So we'll do search. We need a search one. So node star search, and we'll search the root, and we need to search by some key, right? Constant star key. Okie dokie. Alright. So when you're searching, right? Let me draw another diagram somewhere. Maybe I can reuse this. Let's reuse this for now. And let's say 5 was here. Suppose we wanted to find the element 5. How would you think about it? How would you go about doing this, right? How do we find 5? Well, obviously we know the root is the entry point. And so all you have to do, it's binary search. It's quite literally binary search that we're doing. And this is why binary trees are a natural extension to binary search, really. So what's going to happen then, right, is that you're going to compare, right, the key, or 5, with the root node. Okay, well, 5 is less than 10. Okay, so go to the left, right? And then you check, okay, well, have we found the root node? If not, if it was deeper down, then, right, you would continue traversing in that order. Okay, you would say go left, go right, go left, go right. Hopefully you understand what's going on there, until you find a match. And if you didn't find a match, well, then it means that, okay, that node does not exist, okay, or that key does not exist. Alright, so let's come up back here and try to implement that. So we're going to need, so we're going to need string compare, right? So we'll say integer x is equal to string compare, right? And we're going to do the regular comparison. So we're going to just check the root node against the key, right? So we're going to check root dot first name against key, right? And so what this is going to do is greater than 1 if root, oh, I need to be commenting this, greater than 1 if the root is greater than key. Okay, which implies we have to search to the left. Okay, so if the root is greater than the key, then it means the value we're looking for, or the key, must be to the left of the root, right? Hopefully that's clear. So the first thing you should do, obviously, is see, right? Oops. Back here. So if x is equal to 0, it means we have a match, right? So you just return the root, like so. Then we'll say if x is greater than 1, so this is the case where we have to search to the left, right? If x is greater than 1, then we'll say root is equal to root dot left. So we're quite literally, it's very similar to traversing a linked list, where we're saying like current is equal to current dot left, or sorry, current is equal to current dot next, rather, right? Traversing root is equal to root dot left. So go to the left, right? So if the root is greater than the key, okay, it means that the key is to the left of the root, right? So we go root is equal to root dot left. Hopefully that makes sense to you. And if not, you could do it the other way around as well, whatever makes sense to you. Oh, and it's not greater than 1, by the way, it's greater than 0. Then we say root is equal to, same, go the opposite direction now, root is equal to root dot right. And then obviously we need a loop here, so we'll just say while, and so while root Well, we have a root value. We'll run this bit of code here. Okay, so as soon as it comes across a null, then yeah. So then here we're just going to return root, like so. So if it doesn't find anything, then if it's null, we know that it didn't find something. Okay. So I hope this is okay. Let's go ahead and test it. This is an iterative approach, and my sense tells me that this is okay. Alright, so we're going to do searching after level order. So we're just gonna search for a C maybe. So we'll say search, and we'll search root, and we're gonna search for the key C. And remember the search is returning something, right? So we'll just say it's returning a node pointer. So we'll say node star value is equal to search. So it should be inside of value, and then we'll say if value, right? If we found something, then just print it out. We found some s. Then we'll say value dot first name. So let's see if this works. So it didn't work, and we have to figure out why. Yeah, it seems a bit strange that this wouldn't work, but yeah, we'll see. And then we'll say if not value, so we need to see if it's not finding that value. Let's printf not found. So we're gonna have to do a bit of debugging here. So it's printing not found, so it's not finding this. It's not finding this character C, but we know it's in here, right? We literally put it in here. So let's try another one. Let's try B. Whoops! It just might be in the logic somewhere. Okay, it found B, but it didn't find C for some strange reason. Yeah. And let me take a look at how this structure looks like. So it's B, A, C. Okay, so what's going to happen, let me just come back here and walk through this code. So it's going to compare against the root dot first name to the key, right? And it's going to return 1 if the root is greater than the key, right? And so obviously if the root is greater than the key, then the key lies to the left of the root, right? So if x is greater than 0, then root should be equal to root dot left, which makes sense to me. And then, yeah, if x is less than 0, then root should be equal to root dot right. So I don't see why that's an issue there. Yeah, it's quite strange to me. And it was able to find A as well, so not found. So it was not able to find A either. So we've got to do a bit of debugging here, and I think it's going to be helpful to print out what x is. So we'll say print. Let's see what x turns out to be here. So printf %d, and we'll print x. So x is 1, right? So we're trying to find A, right? So it's going to string compare against the root, which should be B, right? The root is B, against A, right? And so it's returning 1, which means it's saying that B is greater than A, which makes sense, right? B is greater than A. Then while there is a root, okay, then, okay, if we found the match, you return the root straight away. Otherwise, if it's greater than, in this case, this is the case that's running, right, because we got 1, then root is equal to root dot left, and we're trying to find the value A, and so A is to the left, so I don't know what's going on here. Maybe could be that, but I doubt that's the case though, but we'll see. I don't see why. Yeah, it's not the case. Maybe it's because it's returning the null root. Ah, yeah, it's returning null every single time. I think that's the issue here. So this should quite literally just do the same thing though. Yeah. Yeah, but in the case that it's null, right? As soon as root becomes null, how do we fix that? How do we fix that? Yeah, that's the trouble. So what I suspect is happening here, right, is that it's coming to, it's starting here, right, and then it's starting off with B. So it's starting off with B, and then it's saying, okay, well, it's comparing B to the key, right, and it's saying, well, it's returning 1. So it's comparing root dot first name, B, to the key, and it's saying, well, this is greater than the key. How is that greater than the key? Yeah, it's greater than the key. Well, lexicographically it is greater than the key, which is why I prefer working with numbers. Okay, so yeah, we have to go to the left of the tree, right? So, yes, root is great. So root is equal to root dot left. So we've gone to the left of the tree now, and so we're at A, right? So we're where we need to be. Oh, that's so dumb. And so what's happening, right, is that we're actually not doing the comparison every single time we update. And so it didn't find the base case where x is equal to 0. That is quite silly, isn't it? So, but at least we were able to figure that out. So yeah, we found A now. Great. So don't make that mistake. Always make sure you're checking for your base case. Yeah, but that was a very silly mistake. But sometimes you do make mistakes, right? And you just gotta figure out what's going on and get it right. So there, we got it right. Okay, let's do another example. Let's search for C again. And so we found C this time. Alright, so we're good to go. Great. So we can delete this now. So we got our search function working. Now let's go back to our deletion. So now that we can find nodes, it'll help us with our deletion. Great. So we were back to the case where we have no children, right? So we want to delete this guy. So first of all, we want to delete this node, so we have to search for the node, right? So we found the node that we want to delete. Great. And this is where having access to the parent is very important. Do you remember in our linked list operations, right, that we had to traverse all the way and stop just prior to the node that we wanted to delete? If we wanted to delete this guy, we needed to stop just prior, right? And so this is why in some implementations it's better to have a forward and a backwards pointer, right? So you're also pointing back to the parent, right? So here we quite literally do have a backwards pointer to the parent. So we have the parent, so we don't have to do any traversal or anything, you know, any kind of shenanigans like that. We know who the parent is, okay? So all you have to do is say, okay, figure out, right, whether this node is to the left of the parent or to the right of the parent. And we know how to do that. We're going to string compare, right? And we're going to figure out whether it's greater than the parent or less than the parent, so we know whether it's going to go to the left or to the right, okay? And then based on that, we're going to say parent.left or parent.right is going to be equal to null. Okay, we just set it equal to null and we free this off. It's as simple as that for this case here. Okay, so this is case 1. And then there's another fringe case as well, though you have to consider, and there's always the fringe case where the node you're trying to delete is the root node itself, like this, okay? And so in this case, right, and this fringe case now is where you need a pointer, right? So you have to modify the root node itself, right? You need to, obviously we can search for this, we'll search for this node and we'll find it, and we can free it off, right? But we need a way to modify the head of our binary search tree, or the root of our binary search tree. And if you remember again from our linked list implementation, we need a pointer to a pointer, and I already explained why there. I don't want to go too much in depth again on that. So you should know why we need a pointer to a pointer. Okay? So our delete function prototype is going to be taking a pointer to a pointer for the root node. Alright, so we'll be able to set the root node internally to null. Okay, we'll be able to set that to null. And so that'll essentially reset our binary search tree. Okay, so let's just go ahead and implement this case, and then we'll move on from there. So we'll say node star. I don't think we need to return anything, do we? No, I don't think so. Delete. And yeah, so we're going to be deleting. So I said before, we're taking a pointer to the root, and we're going to need the key, right? Constant, the key that we're deleting. Alright, great. And so obviously the first thing you have to do is search, right? And so obviously though, I think you should check for the very beginning. So if doesn't matter at all. So we'll just say node star node, right, is equal to, and then we'll search for, then we dereference the root, right? Okay, and hopefully you understand what this is doing. This is giving us the root structure itself, and that node is giving us that node itself, because we have a pointer to a pointer, right? So by dereferencing this, it takes us to that node. And again, if that doesn't make sense to you, go back to the linked list tutorial. I explained that at length there. Alright, so, and then we need the key, obviously. So you search for the key, and you put it in there. Okay. Oh. And then I should say if you did find the node, or if not node, then we'll just return straight away. Just break out, don't do anything at all. Alright, and then so we have case 1. I'll say case 1 when there are no children, or child nodes, well, no children. Okay. So the way we check this is that we'll say if, right? If node dot left and node dot right, then we just say not. So if there's no right node, and if there's no left node on the node that we searched for, then we know that this is the case when that node has no children, right? Or they call it a leaf node, right? So this one's a leaf node, or an outermost node then, right? And so what are we going to do? Well, we have the fringe case, so we can cover the fringe case later, so let's just cover the general case first, right? And so let's go back to our general case, right? And so we said that in the general case, we need to figure out then, first of all, whether the node, right, that we're trying to delete is to the left of the parent or to the right of the parent. And so we can do that quite easily with string compare. So we'll say integer x is equal to string compare, right? And then we're just going to compare it with the parent. So we'll say node dot parent dot fname, right? And then we'll say node dot fname. Okay. And so what this is going to do is, if the parent node is greater, return greater than 0. Okay? Otherwise, then, yeah, it's going to return less than 0. And if it's equal, then, okay, that's not going to happen. So, yeah. So now here we'll say if x is greater than 0, right? So if x is greater than 0, we know that the parent node is greater than, right? So it has to go to the left, right? Okay, so we know that it's this case here that we have here. So it's to the left. So then we'll say parent, right? Node.parent.left is null, right? So node.parent.left is equal to null. Okay? So we found the parent node, and then we went to the left of it, and we set that equal to null. So hopefully that makes sense to you. So we went up to the parent, and then we set this equal to null. And we need a free node function now, so we'll say free node, like so. Okay, and then when you're done, you can just return out. So let's implement this free node function. It's quite simple, really. And so we'll just say void free node, node that we're trying to free, and you'll see that this is quite literally the same thing as in order traversal. So we'll say free node, node dot left. Or actually no, that's for when we're freeing the entire binary search tree. If we're just freeing a singular node, then we're just going to have to say free node dot left. Well, let's go with the first name and the last name first. Right, and then we can free the entire node like so. Yes, I think this is fine. Yeah, because we're just freeing a single node, and it's a good thing that I brought that up as well. I do need this function here. Free BST, free the entire binary search tree. It's very good practice. So start root, so you just give it the root, right? And then you use the recursive implementation. So you call free BST on node.left, and you should already know what this is doing from the in order traversal. And then you go free BST node dot right, like so. Then you free node root, like so. Okay. So you travel all the way to the left, and then you travel all the way to the right, and then you come up and you just free all the nodes. And I think this has to be, there needs to be a base case in here. While the root exists. So I'll cut this and I'll put this below the free node function. Let's test and ensure that we don't have any issues there. Free BST, oops. Throw the root, root. My keyboard's just really malfunctioning at this point. Oh, that's because we have this incomplete bit of function here, but it's also complaining about something. So what is it complaining about? This here. Shouldn't be. We're not calling it, are we? So it's not node.left, it's root.left. So we're getting a seg fault here. Yeah, so I'm wondering why it is that we're getting a seg fault. So while root so let me try to figure out. So you go to the leftmost, and then you come up back to the rightmost. Then you should just be able to free those nodes off just like that. Not sure why this would be seg faulting. This is quite literally the same thing as root, by the way, so it shouldn't. And just to confirm that this is the issue, let me just comment this out. Yeah, so that's the issue here. Okay, we'll come back to this in a second. It's a bit puzzling to me though why this isn't working. So we're collecting the root, right, and then we're calling the function recursively on itself to the left, so it's going to go all the way to the left. And then once it reached the leftmost case, right, where it's null, it's going to come up back to the parent. And maybe it's because I'm saying, yeah, we need an if statement, not a while loop. I believe this is the issue. Oh, I need to uncomment here. Because remember, it's quite literally just a mirror implementation to our in order traversal. Yeah, that was the issue, because we had a while loop there, so it just kept going and going. Yeah, so it would seg fault eventually. So yeah, So what's going to happen, right? Very much as with our in-order traversal, it's going to come all the way down to the left, right? And then it's going to encounter a case where the root is null. It's going to throw that back to the caller, and then it's going to go to the right, right? And then traverse whatever is to the right of that subtree. And then it's going to eventually make its way up back. And then once it's done, right, with left and right subtree, then you free that node. Yeah. So that makes quite a bit of sense to me. So this should be working fine now. Okay. So we can come back peacefully to our delete, and I kind of lost my train of thought a bit. So right, so we covered when it's greater than 0. Now we need to cover when it's less than 0. So when it's greater than 0, we go to it's to the left, right? But when it's less than 0, then we have to go to the right. So it'll be node dot parent dot right is equal to null, and then we can free the node. Then we can just return like this. And now we need to cover the fringe case I was telling you about, though, where if the node we're trying to delete then is the root node, and the root node has no children, right? So fringe case we need to check for is if we'll say here if node is equal to root, so we can just check. Or no, we don't need to do that. We can just say, right, because remember, we know by default then that the root node has no parent, so we'll say if it doesn't have a parent, right, then we know it's a root node. We don't have to do any fancy anything. We don't have to do anything fancy here at all. So if it doesn't have a parent, then okay, what did we say we need to do? So in this case, we just need to update the head of the root, right? So we'll say star root is equal to null, and then we free the node off like so. Yeah, I think this is fine. Then we just break up like so. Okay, so this should be fine now. So we've covered the first. So we've got 3 cases we need to cover. We've covered the first case here. So let's test that it works. I'm gonna have to delete some of these though to make sure that it does. So let's do the first case where the root is just a root node we're trying to delete with no children. And so we'll say just delete. We need to give it a pointer to a pointer, so root, and then we'll delete B. Make sure to see here. The left side of semicolon. If not parent, node dot parent. Alright, so I think we were able to successfully delete that, but we need to test this a bit more robustly. So I'm just going to yank and paste a couple of times. I'm going to put A in, I'm going to put B in, and yeah, so that's it really. And we're going to delete B, right, because we know B wouldn't have any children. And so it should print A and B, and then it should, let's come back down here. So let's yank this level order again, and oops, let's paste it here. So it should print A, B, and then it should just print A alone. There we go, so A, B, and A alone. So we successfully deleted B. And so we know it's working then. And then, okay, we can just, I'm wondering what's going to happen though if I try to delete A off and then print it. It shouldn't, yeah, it's not printing anything, so that means there's nothing there. So yeah, we're good to go. So we covered that case. Now we need to cover the next case, and that's this one here, where the node we're trying to delete has 1 child at least, right? And then the other cases, the node we're trying to delete has 2 children to it. But we'll start with this one here. And this is very similar again to the linked list implementation. So what you're going to do, right, so suppose we wanted to delete this node here, wanted to get rid of this guy here, then all we have to do then is, first of all, figure out which node it has, right? And we would know, obviously. We would know, because we're going to need 2 special cases for this then, right? One where we need to know, essentially, what I'm trying to say is the child of this node, which child it has a node in. Is it to the left of the parent, or is it to the right of the parent? And it's very easy to check as well, right? So what we're going to do, if it's to the left like this, is we're just going to bypass around like so. So we're going to say node.parent, right, dot left. So we obviously need to know if the child is to the left or to the right of the parent, right? It's just as like we were doing up here, right? If the child is to the left or to the right of the parent. In this case, it's to the left of the parent, so we'll say parent node.parent dot left, right, is equal to node dot left. Okay, that's how we would do that here. And then we free this node off like so, and this would be gone, and everything else, the structure would remain intact. All right, and then there's obviously the case now where the node we're trying to delete is the root node, right? So if we're trying to delete the root node and it had at least one child, like so, right, what we would do then is update the root pointer, right, to be whatever this value is here, okay? So, and whether or not it was to the left or to the right. So update this to be node.left, okay? So yeah, that's all it is really. So this guy here would become, whatever child was in here would become the new head then, okay? And then we set the parent and all. Obviously the root node can't have a parent. So I'll show you how this works in a second, and you'll see. So we've got the case 1, now let's work on case 2. Case 2, and don't worry, we're getting close to finishing. Case 3, it's probably the most difficult case, but it's the easiest one to implement, so in my opinion. So case 3, where there is at least one child. Okay, let's get into this. So how would we know, right? So obviously we can say then if node.left and not node.right. So this is the case then where there is a left child node, right? But there's no right child node. And then we need the other case as well. We need to check the other case where not node.left and node.right. So this is the other case where, okay, there is no left child, but there's a right child, and this one there is a left child, but there's no right child. Okay, so, but we'll work with this example here first, where the node we're trying to delete is it has a left child, right? So, okay, what are we doing here then? Oh, oops. So again, we need to do integer x. So what I can do then is just come up here and just yoink this. There we go. So we got the string compare here, right? And so if, oops, come all the way back here. So if x is greater than 0, come down here. Alright, so if x is greater than 0, then we know that the parent node is greater, right? The parent node is essentially greater, so this node belongs to the left of the parent node, right? So this node is to the left of the parent node, right? So we know, right, that this node has a left child to it as well, right? And so what we would say then is parent dot left, right? Because this node originally belonged to the left of the parent node. So parent dot left, so node dot parent dot left, right, is equal to, so we have to replace this value essentially. So, and then it has to be equal to this guy here, right? Is that equal to node dot left? And we're saying node dot left because we know, right, this is the case where there's a left child but no right child. So we don't have to do any calculations there. We already know. Okay? And then we just free the node and we return. Right, so. Okay, and then this here would be just the opposite case. Right. So you would say if so this is if x is greater than 0, we need the other one here as well. So if x is less than 0. And so if x is less than 0, right, it means that this was over here instead. It was over here instead, right? It was to the right, okay? Okay, so that means that it was greater than the parent node. And so then we would say node.parent.right is equal to node.left. Right? Because remember, we know it's a left node. The left child then. It has a left child. That's what we know. So we free the node. Hopefully this makes sense to you. And then we return. Okay? And yeah. So we do the same thing here again. So if x is greater than 0. And set up the other case as well. If x is less than 0. And yeah. So, and now here it's just a bit reversed now. So here we would say node.parent.right is equal to node.right instead, right? So it's the same thing as up here, but only thing now we're changing is the node.right instead of node.left, because we know that the it's node.right, right? The current node we're trying to delete has a right child, doesn't have a left child. So node.parent.right, in this case, we're trying to delete something here, right? It would be node.parent.right if it had something to the right of it, like so, right? With this, and this was null. Okay, so this is the other case then, right? Okay, so where am I? Node.parent.right. Yeah, it's equal to node.right, and then we just free the node. Return. And then this is the other case now. So we're literally covering all the cases then, right? And I hope you understand what the cases are, right? So the case could either be that the node was to the left of its parent, right? Or the node was to the right of its parent, right? That's what we're calculating here with string compare to try and figure out. And then we already know that the node, where the node has its child then, right? Is it to the left or is it to the right? And that's here, in this picture, okay? So that's the point I'm trying to get across to you. Okay, and so this would just be the other part, so node.parent. Alright. No, dot left. So if it's greater than 0, no, it has to be left. Yeah. Okay. Yeah, if it's greater than 0, then it's to the left. And otherwise, it's to the right. And let me just double check this. So string compare, so if the parent is greater, right, it's going to return 0. So obviously if the parent node is greater than the node that we're trying to delete, then we know that that node has to go to the left, right? So yes, so it would be node.parent.left, right? So that's how we figure that out. So node.parent.left would be equal to node.right. So yeah, we've successfully bypassed it. So node.parent.left, so we're referring to this position here, is equal to, so this position is equal to, right, node dot either left or right, depending on where this position is, right? I hope you understand what that expression is saying, right? And so the tree now, the new tree would look like this. It would just look like this, right? It would look like that, and this node would disappear. This node would be gone. Okay. So I hope I did a decent job of explaining what that case was. Alright, and so let's try it out, obviously. So, doing this. Did I cover? No, I didn't cover the fringe case. So remember I said there was a fringe case as well, though. Is what happens, right, when the node we're trying to delete is the parent node. Right, so suppose we wanted to delete the parent node here. So we're going to have to say, we check this at the top, obviously, every time. So we'll say if node.parent, so if the node doesn't have a parent, then we know we're trying to delete a root node here. And so what we'd have to do is update we have to figure out then whether it's to the left or to the right that this node is. So if the node doesn't have a parent, the first thing we need to do is check. Yeah, we can do that in both cases though, so we already know. Yeah, so this is the case where it's to the left. So this is this case here where there's a left child but there's no right child. And so what we do is we can say node.parent, so root, we update the root to be equal to node.parent dot left, and then we free the current node. You break out. Okay, so the new root is going to be this node, the node we're trying to delete. No, that doesn't make sense. The node we're trying to delete is the root node itself, so it has to be node.left. It just has to be node.left, not the parent. Okay, so we're deleting the root node, and we know that there's only a child to the left of it, so this has to become the new successor, essentially. So the new root is going to be node.left, and we free the node and it'll return. Right, and then we come over here, copy this, and we do the fringe case here as well. So in this case though, it's just node.right instead. This should work now. Alright, so that's our base case covered. So we've gone A, B, and C. Okay, so this should be, go here, so just print A, B, and C. Now let's try to delete, give a memory location of the root, and let's delete B, right, because we know B has a single child. And then let's do level order. I'm getting very tired, but we're almost there. Okay, so we got A, B, C, and then we successfully managed to delete that value, B, off. And now let's try the other case, right? So B is gone now, so we know A would be, let's try to delete A. A would be the root node, right? So now C alone should be left. Yeah, there we go, A, B, C, and C. So good. That works fine. Alright then. So now there's the last case. The last case we have to cover. And that is what to do, right, when the node you're trying to delete has two children, like so. What do you do? Suppose I wanted to delete this node here. Right, what do I have to do? So this is what you do, obviously. So the first thing is you search for the node, get the pointer, right? Get the pointer to the node. Then what you do is you find the minimum of the right subtree of that said node. Okay, so the right subtree of this node that we're trying to delete is this subtree here. Let me get a different color. Let me use the highlighter. So that's this subtree here. Find the minimum node of this subtree. The minimum node of this subtree would be this guy here. Okay? And so then what you do then is you copy over this value here. Okay? And then you delete this value off. That's what you do. And so then what we've done essentially is reduce this problem, right? And so if you can imagine, then we've copied this value up here, and we didn't break the structure of the binary search tree, because the value, right, on the right, the minimum value of the right subtree, right, is going to be less than all these other values here, right, obviously. So if we put this up here, it doesn't break the property of the binary search tree. It's still less than all these other values, right? So everything here is greater than this value then, okay, is what I'm trying to say. And then we've reduced this problem now. So if we delete this off, we duplicate it and put it up here and delete this off, right? We've reduced the problem down to a case that we can already solve, right? I hope you see that. Then we've managed to reduce the problem down into a general case that we've already seen, where the node we're trying to delete, then it's pretty much gone. Are we? Yeah. So yeah, that's it. So instead of deleting it from here, right, we replaced it then. That's what we did. We replaced it. And the way we reduced that problem was by finding the minimum of the right subtree. And how do we know that this reduced the problem for us, right? Because we know that the minimum of the right subtree, right, this node here that we're deleting, right, which is why I said when we reduce the problem, this node that we're deleting here now, because we duplicated it up here and we need to delete it down here, this node we know can't have a left subchild as well. We know it might have some value to the right of it, but we don't care, because if a value is to the right of it, then it's not the minimum value in the right subtree now, is it? And if there was a value to the left of it, then it's not the minimum value in the tree. Now is it then? Yeah? We just have to keep going left. And so quite literally, when you find the minimum value in the right subtree, you know you've reduced the problem down to something we can solve. So you can recursively call the delete function on itself to clear this node off, right? So you delete this, and this would link now to this guy here, right? And then you copy that value up here. So I hope that's clear, but I'll show you in code, and we need to do a little bit of trickery as well. But you'll see it, and hopefully it makes sense to you. And so obviously, since I said that we're going to be doing a recursive call, anytime you're doing a recursive call, it's sensible to have it at the very top. So we'll do case 3 now, where there are 2 children nodes, like so. Alright, so hopefully we're close to the promised land. Okay. So we'll say, sorry, my brain is just not braining. I don't know, very long day. But yeah, so case 3 is when the node dot left and node dot right. Okay, so we've got 2 children node, and then so the first thing we said we need to do was we need to find the minimum, right? So we need a find minimum function. So node star find min and node star root. We'll just call it. We'll say node. So find the minimum of some value. And how am I gonna do this? I'm gonna do an iterative approach as well. So I'll say while, right? Node dot left. So while there is something that exists to the left, right, just say node is equal to node dot left. I think it's as simple as that. So you keep marching to the left, right, until you don't find something that's to the left, and then you say return node. So I think this is okay. So this should return as the minimum value of some node, right? And so then what I can say then is minimum node star minimum right of right subtree. Minimum right is equal to, and then we call find min, and we need to find the minimum of the value to the right subtree, right? So okay, I said if we were trying to delete this guy, we need to find then node.right, right? The minimum of node.right. Okay, so this serves as the root node or the entry node, right? Because this in and of itself is a binary search tree as well, right? It's just abstractions that you're doing here. So we find the minimum of this binary search tree, okay? So that's the root node there. So find minimum of, and the root node is node.right, okay? So this would return us the minimum node, I hope. So, okay, we said the first thing we had to do was search for the node, get the pointer. We already done that. Find the minimum of the right subtree. And now I'm going to copy over the values. I'm not going to free anything yet. I'll copy the values, and you'll see why in a second. So first star, first name, copy, is equal to CP, is equal to, then copy, yeah, that should be fine. And I'll use string duplicate. Yeah, string duplicate is perfect here. String duplicate, and it has to be minimum right dot first name. So we're copying the relevant information, and you might, in your implementation or whatever implementation you're doing, you might have a lot more real world information, right, to model, but I'm just using first and last name for now, but you'll be copying over all your relevant information. So you copy the first name, copy the last name, so you've got that stored now, right? And so I hope you know what string duplicate is doing, by the way. It's just going to make a duplicate of the string and return a pointer to it, okay? So that's all that's doing. And then now what we do is we delete, right, this node, because we don't want to copy the values here straight away, right? Suppose this had, hypothetically speaking, this had the value 17 here, right? And then we copied it here right away. We wouldn't be able to delete this 17 out, because when we called the delete function recursively on itself, the first thing it's going to do is search for 17 by key, right? And it's going to try to delete this node here, which is not what we want. We want this guy gone, right? Because we managed to reduce the problem down then into a case that we've seen where it only has a single child node, right? So we delete this guy, so we fix this, right? And then remember we stored the values that it has, the relevant values. So then when we finish deleting this guy off, then we can come up here and change this value essentially. Okay, so that's what we're doing here. So then we're going to call the delete function now recursively, now that we've copied those values over. And so we're going to delete, and I think I can just give it the root, and because the root is already a pointer to a pointer, so we're good there. And then I need to give it a key. And what am I deleting? I'm deleting the minimum right. Yeah, that's what I'm deleting, right? Let me just double check. Yep, that's what I'm deleting, the minimum right value. Then finally now, when all is said and done there, I can say node dot first name is equal to fname copy, right? And node dot, now we copy over the values, last name copy as well. Then we can just return like so. And I hope this works. I hope we've reached the end because I'm very tired now. So let's see. So we need an example. So I'll do B, and then I'll do A. So A should be to the left, and then I'll do C. So let me make sure this works. So it BAC. What's going on here? It's expecting a key, but I'm not giving it a key, am I? Yeah, you'll have to excuse me. I'm just super duper tired. Where am I? Delete. Here, right? Yeah, we're supposed to be giving minimum right dot first name, right? We have to give it a key, so I think we should be good there. Yeah, so now we've got BAC, and I'm going to try to delete B straight away, right? And you should see it should work, right? And let's try to walk through what would happen in that case, right? We don't have to handle a fringe case in this particular instance, so I don't think so. Maybe we do. Let's see. So it's going to look like this, and we're trying to delete this guy off, right? No, we don't have to handle a fringe case at all. And so what it's going to do is that it's going to search for the node, right? Get the pointer. Then it's going to find the minimum of the right subtree, which is quite literally this guy, right? And then it's going to copy those values somewhere, as we've seen. And then it's going to delete this node off, then move these copied values up here, and that's it. So yeah, that's it. We've managed to successfully, quote unquote, delete this node at the top here, right? And it's just the same. If you imagine we had 10, I don't know, 5 and 11, which we've been using a lot, right? If we were to delete 10 off, right, we would expect 11 to sit on top of 5, right? 11 would be here, and then 5 would be here, which is quite exactly what happens in this case, as you've just seen. So let's run this example and ensure everything is honky-dory. So we did level order, right? And then we'll say delete now. We'll delete the root node. Delete, oops, root, and we're going to delete B. We're going to delete the root node. And then we'll print level order again. And so you should see, right? It starts off as B, A, and C, and so it should be C and B. Sorry, it should be C and A rather. Yeah, B is what we're deleting. So yeah, and it's exactly what I just showed you. Yes. So let me do that again for you one last time. So we had B, A, and C, right? And then what we did was we deleted this guy, right? And then C, and then A ended up here. And hopefully you can follow the algorithm and see what's happening for yourself. And this would work as well for any other general case. So yeah, there you go. That's the 3 cases you need to know when you're deleting. The first case is when you have a leaf node, you have no children. The second case is when you do have one child. And the third case, what we do is we reduce the problem down to either the first or the second case, right? And so hopefully that's clear to you. I know this one was a lot, and yeah, but hopefully you've seen and you've understood rather what we've done. And the reason why I coded this out from the ground up with you as well is I just wanted you to understand in context how this entire binary search tree is operating. Because I think if you don't understand the context or every single little nook and cranny, you're not going to be able to implement an AVL tree, right? In no world will you be able to implement an AVL tree if you don't understand a binary search tree to this level, right? So in the next video, whenever that is, maybe in a couple days from now, whatever, we've got a ton of assignments I need to tidy up as well, and then some work I need to do at the same time. But hopefully you were able to learn something, and if there's anything in this video that was unclear to you, please feel free to make a note in the comments, or if you saw some error in the code somewhere, or you found something wrong with the code, or you want to do an optimization somewhere. By the way, to optimize this code or to make it cleaner, what you should do, I just didn't want to do it because I'm just lazy at this point, but every single time you're allocating memory anywhere, right, you should check that the allocation was done successfully. So for instance, right, where are we? In the create node function somewhere up here. Right, so for instance up here, you should always check, right, you should say if not new node, return null, like this for instance, right? You have, I think it makes sense, this is just clean code, right? If something went wrong with malloc, right, you don't want the program to continue, so you should break out immediately. So it's good practice to do that. So that's a little bit of optimization or improvement you could do. So little things like that, you can feel free to suggest it as well, right? But I think this implementation more or less it's very clean, with some small room for improvement as well. So feel free to improve the code. If you've seen a bug somewhere, feel free to suggest it and how we might fix it. But yeah, and then obviously if you don't understand something, you can let me know in the comment and I'll try my best to help you. So thanks for watching, and you guys have a good one.